So let's look at example number 5 here. At a picnic, Julio reaches into an ice-filled cooler containing 8 regular soft drinks and 5 diet soft drinks. He removes a can, then decides he is not really thirsty and puts it back. That's going to be really big. He's putting it back. What is the probability that Julio and the next person to reach into the cooler both randomly select a regular soft drink? Okay, so here's another keyword that we're looking for, both. Remember, both tells me to multiply. So we're going to multiply these. So I'm going to find the probability of Julio first. Julio getting the regular soft drink. And then I'm going to find the probability of the next person. So next person getting a soft drink. A regular soft drink. And we're going to multiply them together. So I'm going to do this before I determine if it's independent or dependent. So Julio getting a regular soft drink. Well, there are 8 regular soft drinks total. I would have 8 and 5 together, so I have 13 total soft drinks in this cooler. So 13 on the bottom. Now, he got his regular soft drink, but he's going to put it back because he's not thirsty. So if he puts it back, I still have 13 total soft drinks here. And this next person wants a regular soft drink as well, so there's 8 still available for them. So when we multiply these out, I'm going to multiply top times top, bottom times bottom. So I'm going to get 64 out of 169. Divide that in your calculator and you get 0.379. So we need to determine if this is independent or dependent. Remember, if you see puts it back, which means with replacement, or the denominators stay the same, that is an independent problem. So since the denominator stayed the same, my total number didn't change, it's an independent problem. So let's look at number 6 here now. There are 3 cards that are drawn from a standard deck of cards without replacement. Without replacement. Find the probability of drawing a heart, another heart, and a spade in that order. So since we're dealing with 3 cards, I'm doing 3 different probabilities. And because it says the word and, I know I'm going to multiply. So that means to multiply. So the first probability I want to find is the probability of getting a heart. So if you think back to your standard deck of cards, there are 13 hearts out of 52 total cards. Now, I got that heart, and I'm not putting it back. It's going in my back pocket, so it's not going back in the deck of cards. So the probability of getting another heart. Well, now there's only 51 cards, and there's only 12 hearts because I have that one in my back pocket. So then I need the last probability to be a spade. The last card needs to be a spade. Well, that heart, that second heart I got, is also in my back pocket. So there are only 50 cards total, but 13 of them are still spades. I haven't drawn any spades out yet, so I still have 13 of those available. So I know that and tells me to multiply these things across. So I'm going to get 28 on top, and then 132,600 on bottom. When you divide those, you should get close to 0.015. So now let's determine if this is independent or dependent. Looking at those denominators, they are changing, and I see this word without replacement, so that's going to tell me that these are dependent on each other. So number 7 here, there are 3 miniature chocolate bars and 5 peanut butter cups in a candy dish. Liz chooses 2 of them at random to eat. What is the probability that she chooses 2 miniature chocolate bars? So she's choosing 2 of them, so we're going to do 2 probabilities. And we want the first one to be a miniature chocolate bar. Well, there are 3 miniature chocolate bars out of 5 and 3, so 8 total candies in that jar. Now, when we are dealing with candy, more than likely you're going to eat the candy. You're not going to put it back. So we are going to assume anytime we're talking about food that it is not being put back, so it's without replacement. So I picked one, and now that one is no longer there. I ate it, so now I want the second one to be another miniature chocolate bar. Well, if I ate one already, there's only 2 miniature chocolate bars out of 7 total left in that candy dish. So we're going to multiply these together. So I get 6 over 56, which in my calculator when I divide is 0.107. So because we did not replace these and your denominator is changing, we know that this is going to be a dependent problem. All right, example number 8 here. In a state lottery game, each of the 3 cages contains 10 numbered balls. The balls are each labeled with one of the digits from 0 to 9. What is the probability that the first 2 balls drawn will be even and the third one is going to be prime? So we have 3 cages. So we're doing 3 probabilities, and each of them has their own separate cage. So each of them has a ball from 0 to 9. 4, 5, 6, 7, 8, 9. So we want to find the probability that the first 2 balls drawn are going to be even and the third is going to be prime. So if I'm looking at this, and I actually think that you guys have one that says odd. So we're going to find probably that the first 2 balls are going to be odd and then the third one's going to be prime. So first ball being an odd number, well, we have 1, 3, 5, 7, and 9. 1, 3, 5, 7, 9. So that is 5 different numbers out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total balls. Now we see the word and, so and tells me I'm going to multiply. The second ball is also going to be an odd one. And remember, this is a separate cage, so it has nothing to do with the one that we just drew. So I still have 5 out of 10 that are odd. Now I need the last one to be prime. Last one to be prime. So remember, we're looking for numbers that only have 2 factors. So we know that 2, 3, 5 from the number dice are prime. 7 is also prime because it only has 1 and 7. So since this is a separate cage, there's 4 of them out of 10 still total. So we're going to multiply these all across, and I'm going to get 100 divided by 1,000, and that's going to give me 0.1. So now determine if this is independent or dependent. Well, the number in the denominator is not changing, the bottom of my fraction is not changing, and since these are 3 separate cages, they have nothing to do with each other, so this is an independent problem. Last example here, number 9. I have a cage that contains 3 white and 6 brown hamsters. Maggie randomly selects one, puts it back, and then randomly selects another. Remember, puts it back is really big for us. We want to find the probability that both of them, both tells me multiplication, were white. So I want you to try this one on your own, pause the video, and then come back and check your answer with mine. So because of that puts it back, I know that that is an independent problem, which means my denominator and my total options available for me isn't going to change. So I got 3 out of 9 for the first one and 3 out of 9 for the second one. When you multiply them out and then divide, I got 0.111. If you didn't get that answer, please come chat with me before moving on to the practice.